Hey, welcome to Gaffy's Minds. In this video, we're going to be discussing the properties of aldehydes, ketones, and carboxylic acids. We previously learned that all of these molecules have something in common, and that is that they contain this carbonyl group, C double bond O. Now, the molecules are different in the rest of their structure in that some of them may have other groups attached, or some of them may have carbon chains attached, some of them may have hydrogens attached, but they all have this in common that they have the carbonyl group. Now, if we take a closer look at the carbonyl group and we consider the electronegativities of the C and the O, what we'll figure out is that the O is very much more electronegativity than carbon, and it drags electrons towards itself. So for the bond, the electrons are not shared equally. The oxygen will be slightly negative and the carbon will be slightly positive. Delta positive, delta negative. Okay, so we say that this here gives the molecule a polar part. Okay, so this is our polar carbonyl group. So what impact does this have on intermolecular forces? Well, if we were to draw another molecule nearby that's similar, that also has a carbonyl group, so this could be another ketone, another aldehyde, another carboxylic acid, well, we know if it's got the carbonyl group, then it's in the same situation where we've got a delta negative oxygen and a delta positive carbon. And what this means is that there's going to be an attraction between this delta negative oxygen and this delta positive carbon on the next molecule. So this here is what we call an intermolecular force. Now this is not new, this is revision for us, but we're seeing how something we've learned before is related to what we're currently studying in organic chemistry. So intermolecular forces in all of these molecules, carboxylic acids, aldehydes, and ketones, the intermolecular forces are all between the carbonyl groups, and the type of intermolecular force they're going to be is what we call dipole-dipole. That's because we have two dipoles here, partially charges attracting each other. So this is a dipole-dipole intermolecular force. Now, the reason why this is not hydrogen bonding is because hydrogen bonding has a very specific meaning. It's a very specific type of dipole-dipole force where we're interacting a delta positive hydrogen with a delta negative NO or F. Now, in this case, we do have a delta negative O. We have a delta negative O, but it's not combining, or it's not being attracted to a delta positive H. It's been attracted to a delta positive C. So this here is not hydrogen bonding. It's dipole-dipole interaction. So thinking about the boiling points and melting points, then if we consider aldehydes and ketones, which have the carbonyl group here, then if we consider and we compare them to say they're similar alkanes or alkenes, well, those only have van der Waals forces. There's no polar groups in an alkane, for example. Okay, so these only have van der Waals forces. Whereas these new molecules here with the carbonyl group, these are going to have higher melting and boiling points than alkanes. So higher than alkanes. Actually, I should put in higher MP and BP than alkanes, or alkenes or alkynes, any of those that don't have this polar group. And of course, this will be the same for the ketones. They have higher MPs and BPs than alkanes or alkenes. Okay, so that's something to note. That's the first property that we're looking at is melting and boiling points, and they will be higher than alkanes because alkanes only have van der Waals forces. What about the carboxylic acids, and why have I not touched on those yet? Well, the reason why I haven't touched on those yet is because they actually are a little bit different. In that carboxylic acids have a C double bond O, but they also have this OH group attached. Okay, so this is our carboxylic acid. And of course, we know that this is polar, delta negative O and a delta positive H. But there's another polar bond going on here, and that's this OH bond down here. Okay, in that the O will drag electrons towards itself and make this also a delta negative O, and that will make this a delta positive hydrogen. So electrons get dragged towards that oxygen and electrons get dragged towards that oxygen. So overall here, we have a delta negative O up on the carbonyl group, and then we have a delta positive H on the alcohol group or the OH group. Now, if we line this up with another carboxylic acid, we'll see what happens up here. So I'm going to draw this the opposite way around. Here's the H and the O on top this time. And there's the carbon and the double bond on the bottom this time. Okay. So again, it's exactly like before. We've got a delta negative O and a delta positive H. And that's the same as we had down here. Remember, all I've done is flip the molecule upside down here, the second molecule. So we know the electrons are getting dragged that way, and they're also getting dragged this way from the carbon. So this is a delta negative O and a delta positive C. Now, the difference that we see here is now we have a delta negative O intermolecular bonding or intermolecular force with a delta positive H. And we have that again down here. Look, a delta positive H with a delta negative O. Now, when we have a delta positive H with a delta negative O, N or F, we have what we call a hydrogen bond. So the carboxylic acids actually have what we call double hydrogen bonding. We have one here, a H bond, and we have another H bond up here. Now, H bonding is even stronger than dipole-dipole. It's a special type of dipole-dipole that's stronger than dipole-dipole. So carboxylic acids, because of this double hydrogen bonding, they are going to be higher than ketones or aldehydes. So higher BPs or MPs than aldehydes or ketones. Sorry, aldehydes and ketones. And that's because of the double hydrogen bonding. So there's the first property that we've looked at, is their melting points and boiling points. Overall, let's summarize. Aldehydes and ketones have definitely got higher melting and boiling points than their corresponding alkanes. And that's because these have dipole-dipole forces due to the carbonyl group. But the carboxylic acid comes in at by far the highest melting and boiling points out of these three because of the double hydrogen bonding that it's got going on. So that would be the reason why that carboxylic acids would have higher melting points and boiling points than the aldehydes and ketones. I suppose if we were to compare the aldehydes and ketones and say, well, which one of these is going to have a higher melting point and boiling point? Well, it probably comes down to the idea of where is the carbonyl group. So if we took, for example, both molecules, an aldehyde and a ketone, if we take that have 3 carbons. So let's draw the aldehyde first of all. Here it is here. Here's the C double bond O on the end carbon. That's always the way it is for an aldehyde. And this will be propanol. And we're comparing it with propanone, which has the C double bond O on the middle carbon. Well, there won't be much difference in these boiling points, but there will be a slight difference in that this one here, because we've got the delta negative on the end atom, this is kind of better able to interact with the delta positive on another carbon because it's at the end, whereas this one kind of, the polar group is getting blocked a little bit by the carbons on both sides. So both of them have this polar group. Here it is. There's a polar group and there's a polar group, but it gives it a little bit better access when it's on the end, so it can intermolecular bond with its neighboring molecule. This one's a little bit more crowded out by the carbons on both sides. So I'd expect the aldehydes to be a little bit higher and these to be a little bit lower, but carboxylic acid will be higher than both of them. Right, the second property we're going to look at is, are they soluble in water? And we know that water is a polar molecule. Okay, we learned this before. We've got 2 hydrogens and an oxygen. It's polar because we've got delta negative oxygen, delta positive hydrogens, and the shape of the molecule means that the dipoles don't cancel out. So this is a polar molecule. And we know the general rule is that like dissolves like. That's the general rule, like dissolves like. So we know that water will dissolve molecules that are also polar. So the question is are these molecules polar or not? And the answer is it depends. We said before that this group here, the carbonyl group, is a polar group. So generally, we might think that any molecule that has the C double bond O in it will be polar. The problem is that the bigger the molecule is, or the bigger the tail is, so say we've got a molecule here that has a C double bond O and a H, so that's a polar group right here. This part of the molecule is polar. But if you've got this really long chain attached to it then, so say 7 carbons long, well, all of this is non-polar. And the non-polar bit is much bigger than the polar bit. So basically the idea here is that the longer the non-polar bit, the less polar the molecule is overall. There is this little polar bit at the end, so there is this bit, but generally it's the short-chained molecules that are the most polar. All right, so basically what's going to occur here is that short-chained aldehydes and ketones will be soluble. Soluble when short. And the same here, soluble when short. But that as we make the chains longer, the non-polar part kind of overshadows the polar bit and stops it being polar. So the longer the chain, basically, so if we the longer the chain length, the lower the solubility. That's the relationship here. And the reason is that the non-polar bit kind of cancels out the polar part of the molecule. Shorter chain, higher solubility. Okay. Carboxylic acids are a little bit different. And that is because they can hydrogen bond with the water, okay, which gives it kind of an extra level of stability. So if we consider the carboxylic acid, COOOH, we know that this OH group, we know that this OH group here is delta positive hydrogen, delta negative oxygen. And if we consider a water molecule beside that, we know we've got here we go. We know that we've got a delta negative oxygen and a delta positive hydrogen. Okay, and we know then that this is going to be an intermolecular force that is a hydrogen bond. And anything that can hydrogen bond with water is always going to be soluble. So again, carboxylic acid is generally much more, even more soluble in water than the aldehydes and ketones. So higher solubility in water. All right, so taking that, we're just going to go back over here for a second. I'm going to have a quick read and make sure I haven't forgotten anything. So both aldehydes and ketones have the carbonyl group in their molecules, and this is known as, so the C double bond O is known as the carbonyl group. The C double bond O group is polar, which makes the overall molecule makes it polar. This means aldehydes and ketones have dipole-dipole intermolecular forces. The boiling points of aldehydes and ketones are higher than their respective alkanes due to the dipole-dipole forces between the molecules being stronger than the weak van der Waals forces that are between alkane molecules. So alkanes only have only have van der Waals, whereas all of these molecules at the carbonyl group have dipole-dipole. The boiling points of aldehydes are lower than the corresponding alcohols due to the dipole-dipole forces between aldehyde molecules being weaker than hydrogen bonding that occurs between alcohol molecules. So if we consider the alcohols and we consider, say, the methanol, it's got the OH group. So this is methanol, 3 hydrogens and an OH group. Again, is delta positive hydrogen, delta negative oxygen. And of course, that means that when it's beside another alcohol molecule, we can get hydrogen bonding happening here, which always increases the boiling point and melting point solubility. So if you've got hydrogen bonding, it's a special case. So alcohols can do hydrogen bonding, aldehydes, ketones can't. Carboxylic acids can as well. All right, so small aldehyde and ketone molecules are soluble in water due to the polar carbonyl group. And here's the relationship. The larger the molecule, the less soluble the molecule is in water, as the effect of the polar group decreases. Carboxylic acids contain a carboxyl group, which is a carbonyl group as above. So it's got this here, but it also has the ol group, the hydroxyl OH group attached as well. Boiling points of carboxylic acids are higher than their respective alkanes, aldehydes, alcohols, and ketones due to the relatively strong double hydrogen bond. So the strongest intermolecular forces exist between the carboxylic acids. This gives them higher boiling points, higher melting points, and better solubility. And we've done that. It says your teacher will draw that double hydrogen bonding. We've done that already. Small carboxylic acids are soluble in water due to the hydrogen bonding. But again, it's the same rule. The longer the chain comes and overshadows that hydrogen bonding, the less soluble the carboxylic acid is in water. Okay, so let's go ahead and let's see, can we fill out this table now? All right, so this should be, sorry, I have to find, it's jumping around on me. Okay, so we're going to be looking at question 54 now. This should be a summary of what we've learned. First of all, complete the following table summarizing the properties of the different homologous series. So the first thing I want you to do is write down homologous series here, homologous series, and take down each of these 1 to 5, doing that now. Okay, so you should have taken down these here. All right, the next thing to do is say what intermolecular force that each one of these has. So that's the next column in the table, filling that out now. Okay, so you should only be playing if you've had a go at these, and we need to get these right before we go on to the boiling point. Okay, so what type of intermolecular forces do alkanes, alkenes, and alkynes have? That would be van der Waals. Alcohols, they have hydrogen bonding because they have the OH group. Ketones, they have dipole-dipole. Aldehydes, dipole-dipole. And carboxylic acids have double H bonding. Well done if you said the double bit, but we definitely all should have got H bonding. Okay, so the next thing is to rank them in terms of the boiling point, where number 1 is not strongest, but highest. Okay, so of course, which are the strongest intermolecular forces here? That will be the highest boiling point, and then work your way down to the lowest. Okay, so let's rank these from 1 to 5, where 1 is the highest boiling point. Pause the video and do that now. Okay, so what we should have done here for boiling point rank is definitely the highest boiling point here is the carboxylic acids with the double hydrogen bonding. So that's going to be number 1. All right, from there, if you haven't tried this already, pause the video and do number 2. Okay, number 2 will be alcohols because they're the ones with single hydrogen bonding. So that's the next highest. After that, then pause the video. What is the next one? Okay, so aldehydes and ketones both have dipole-dipole. I would say that the aldehydes, because the dipole-dipole, the carbonyl groups at the end of the molecule, this makes the boiling point just a tiny bit higher, but there's not much in it. This is definitely 3 and 4, these two. Okay, and then last of all, these only have van der Waals, so these are definitely the lowest. All right, from the solubility rank now, we're going to have a go at ranking them in terms of which ones are the most soluble and which ones are the least soluble. Pause the video, do that now. Okay, it's literally the same thing, guys. 1, 2, 3, 4, and 5. Same thing, okay? So the most soluble carboxylic acids with the double hydrogen bonding, and the least soluble are the alkanes, alkenes, and alkynes because they are completely non-polar. So they won't dissolve at all. Carboxylic acids will dissolve. And again, there is a limit on this. Once the chain gets too big, it becomes less and less polar. Right, we're now going to pause the video and we're working on questions 55 down to 57. We're doing those now. All right, that's it, guys. So you should have been able to do those, hopefully. We will correct them in class the next day. Do make sure you have a copy of that table. I think that's a really good summary table here. All right, so this is something that can definitely help you because questions come up about the properties of these things all the time. We do need to be able to explain why. So definitely it's an important table to have. All right, guys, that's it. I will see you in the next video. Please, if you can, guys, if you can like or comment or share, it would be a help to the channel. So if you can do that, that'd be cool. And I'll see you in the next one.